Hello everyone and welcome to my presentation for driving in dense traffic with model-free reinforcement learning. This was work that I did last summer during an internship at Honda Research Institute, and it has been published at the 2020 IEEE International Conference on Robotics and Automation. In this presentation, I will first introduce the problem that we are interested in to give you an idea of what motivated this work and the kind of results we hope to achieve. I will then go into details about the benchmark for autonomous driving we propose in our work, along with our approach to solve it. We are interested in autonomous driving in dense traffic. If you look at this video of a highway road with dense traffic on it, you will see that merging onto the highway or changing lanes on the road can be very difficult. We as humans typically signal our intent with the use of our turn signals, and when a gap opens up in the lane we want to be in, we execute the lane change maneuver. We cannot simply turn into the lane we want to be in this case, as there is a lot of traffic on the road, and doing so without paying attention to the other vehicles can cause accidents. To state our problem statement succinctly, in this work we want to enable autonomous vehicles to safely and successfully change lanes on the road by negotiating open a gap in the desired lane when there might not exist any. Again, I emphasize that the gap may not exist because we are looking at dense traffic scenarios, and in order to achieve our goal, the vehicle will need to 1. Signal intent, 2. Receive cooperation, and 3. Execute the maneuver. Obviously, there has been a lot of work recently in the field of autonomous driving. We highlight some of these approaches here. Game-theoretic formulations of autonomous driving try to model a value function for driver behaviors that may be considered while optimizing a vehicle trajectory. Imitation learning, reinforcement learning, and end-to-end learning approaches try to learn control policies for autonomous vehicles from data that either emulate observed human driving patterns or obtain high rewards from a specified reward function. Search-based planning approaches for autonomous driving use more traditional motion planning approaches to compute feasible trajectories by using a collision checker in both time and space. While all these different approaches to control autonomous vehicles achieve impressive results, none of them have been shown to work in traffic as dense as what we consider in our work. These approaches also fail to reasonably model the large number of neighboring vehicles in dense traffic, which makes them hard to use out of the box when complex interactions with other drivers on the road are necessary to achieve the goal or the task. Our first major contribution in this paper is a benchmark for driving in dense traffic. At the top here, we show an instantiation of our dense traffic simulation scenario. In our simulations, the ego vehicle, or the vehicle that we are in control of, is visualized in teal color. The other vehicles on the road are in red. The amount of redness of these vehicles indicates how aggressive they are on the road. More red or more aggressive vehicles might not let another vehicle turn or cut or change lanes in front of them. On the contrary, more white or more cooperative vehicles might be willing to make space for another one. The details of how we model this aggressive or cooperative behavior are in our paper. In order to enforce the lane change for the ego vehicle, we randomly place a dead end somewhere in front of it. You could think of this as the end of an on-ramp of a highway. We look at both 2 and 3 lane roadways, but the most important aspect of this benchmark is the slow-moving dense traffic. The other vehicles on the road follow baseline driver models like IDM and mobile, and they are initialized quite close to each other with small desired velocities to emphasize that this is slow-moving dense traffic, and they each have desired lanes that they want to be in. With that in mind, I will now present details in our approach to solve the benchmark. At a high level, we train a vehicle policy using actor-critic reinforcement learning. The actor is trained using proximal policy optimization, and the control policy is parameterized by beta distributions. Our simulator state is converted to occupancy grid-style input observations. I will provide more details in a moment. The control commands or outputs are the vehicle jerk and steering rate. We focus on the continuous control case in our work. We feel that this is important to obtain smooth and realistic vehicle trajectories for acceleration and steering angle, even if it complicates the learning problem little more than the discrete action case. The open source simulator we use and our accompanying benchmark is implemented in Julia, and our reinforcement learning code is in Python with PyTorch. In addition to the occupancy grid style inputs I just mentioned, we also include a feature vector that contains ego vehicle information. The size of the occupancy grid tensor is controlled by the vehicle's field of view. It includes information about on-road occupancy and relative velocities, lateral displacements, and headings of the neighboring cars on the road. The ego vehicle feature vector includes information about the ego vehicle's current state and its desired state with respect to the lane it should be in. We use vehicle jerk and steering rate as our output variables and control commands. They are sampled from independent beta distributions parameterized by a neural network. The beta distribution lets us transform the output to the acceptable limits for these control variables that we show on screen. To make this easier to understand with some pictures, the simulator state shown at the top here is first converted to the occupancy grid style tensor described before. This, along with the ego vehicle feature vector, is fed through our network at every time step. The network outputs parameters for beta distributions for the jerk and steering rate. We can then simply sample from them, transform them to the acceptable limits, and execute them in the simulator. The network itself looks a little something like this. The input observation tensor is first convolved and flattened to a 768-dimensional vector. This is then parsed through both the actor and critic networks, where it is concatenated with the ego vehicle feature vector in the middle. We finally obtain beta distribution parameters and an estimate of the value of the state, as in standard actor-critic architectures. There are several terms in the reward function used to train our policy. First, we have three terms that define the desired behavior we want from our ego vehicle. Second, we penalize large magnitudes of control commands to ensure a level of comfort and smoothness in our vehicle's driving patterns. Finally, we include two additional bonus terms that indicate whether the task was completed successfully and how well the dead end in the road was avoided. We are now ready to see the qualitative and quantitative performance of this approach on our benchmark. While we tested on both 2- and 3-lane roads, for the sake of time and space, we only present results for the more complicated 3-lane roadway. From the ego vehicle's point of view, there's no difference between them. In the video, you see the learned policy quite remarkably and safely change lanes in very dense traffic. We tested our approach in scenarios where all other drivers were cooperative, all of them were aggressive, or as in this video, they were randomly assigned different cooperativeness values. Quantitatively, we far outperform a model predictive control based baseline. The details of this baseline are in our paper. Our policy achieves high success rates and good performance on two other metrics of importance. We have low times to merge or change lanes, and we maintain comfortable distances to other vehicles on the road. In this table on screen, and in the one that follows a couple slides from now, we highlight the best value in each row in green. In a second set of experiments, we implemented random stop-and-go behaviors in other drivers on the road. This was done to reflect the more erratic and unpredictable nature of human drivers on real roads. Again, we trained the same policy on this task, and we can see that we successfully achieve our goal. For this experiment, in addition to the MPC baseline, we present numbers for another baseline from a recent paper published at the 2020 American Control Conference. It is very important to note that while the task is the same, the success criterion used in that work is much looser. The SCAN plus MPC baseline determines success as soon as any part of the ego vehicle enters the desired lane. However, we determine success in our work only when the entirety of the ego vehicle remains in the desired lane for a continuous 5-second period. Quantitatively, we again far outperform the MPC baseline. Also, even with the use of a much stricter success criterion, we are comparable if not better than the new SCAN plus MPC baseline. To summarize, in this work we present two major contributions to the field. We introduce a strict benchmark for driving in dense traffic, and we implement an actor-critic reinforcement learning-based solution for the benchmark that far outperforms baseline models and competes strongly with another new solution to our benchmark, even while using stricter success criteria. The video on the right highlights the versatility of our approach. It is able to successfully learn a policy to move safely across multiple lanes on the road in dense traffic in either direction. Obviously, as with any reinforcement learning-based solution, our policy suffers from not being able to guarantee safe and robust execution in real-world scenarios, and this is something we'd like to address in future work. Thank you for your attention, and thank you for your time.